the slides on the Slack channel, and for the CISA students, I've added you to a specific channel, so you should have access to those slides. So this morning, I'm going to give you a pop quiz, and I'm going to send you the quiz via the chat. So, where are you? Okay. So I've sent you the quiz over the chat. You have about 15 minutes to do it. Then take a picture and then send it to me either, through Slack, preferably.
Sorry, Ali, I didn't hear. When are we supposed to give this?
Now.
Oh, okay.
It's a pop quiz. So do it now, and then you have 15 minutes, and then send it back to me. And I prefer that it's an open mind rather than open book quiz, but okay, so just so everyone's on the same page, I've sent a pop quiz in the chat.
Sorry, Professor.
Yes.
We have to write in copy, yeah?
Yeah.
Okay.
Yeah. So there's a pop quiz in the chat. You have about 15 minutes to answer it and then send it back to me.
Sorry, Professor, I can't see anything in the chat.
You cannot see anything in the chat.
Yeah, I'm also finding trouble downloading it. Could you send it again?
Okay. Strange. It says file biophysics sent successfully. Okay, let me try. I will do something else. I will also put this in the Slack. So that
I think you can send again and they can receive it because maybe they connect late.
Okay. I see. I'll try it again. Does everyone see it now? Okay, very good. In any case, I'll put it also in the Slack.
Sorry, I can't receive. I can't still see it. I don't know what's wrong with it.
Okay, I'm going to put it in the Slack channel then.
Are we using the same Slack channel for molecular dynamics?
Yeah, I've created another channel with called biophysics, and you should be automatically added to it. Okay, fine. All right, so yeah, you have about 15 minutes to finish it up and then send it back to me.
Sorry, should we write on the PDF and?
As you wish, whatever is convenient for you. Okay. Finished? No? Ah, okay. Okay, okay.
Sorry, we will send you Turu's email.
I prefer Slack.
Okay.
Yeah.
But the bio.
Yeah. Or yeah, you can just send it in the general channel or privately. Okay, so we'll stop at 9:30. Okay. So please send what you have. And so we can get started for today's lecture. Here we are. Okay, great. Okay, so we have been discussing sort of going back, moving further away from biology or biophysics and discussing some background concepts that we need in order to make the next step, which is then to go back to the role of solvent and environment in biophysical contexts. So we talked about zero-point energy, we talked about quantum effects. I'll mention a bit about that again today. And I briefly mentioned this interesting paper that I encourage all of you to take a look at on how water can affect the thermodynamics of in the context of chemical reactions. Okay. Okay, so just a reminder, the object that we're talking about are always networks. They're networks of hydrogen bonds, which effectively, at least in the chemistry community, they've been mostly thought of as, electrostatic interactions, essentially. So they're dipole-dipole interactions. And essentially the hydrogen bond arises from differences in electronegativity between that creates a bond dipole on one side, which then allows it to interact with another electronegative atom. And even though it's not called hydrogen bonds are generic throughout biological and physical systems. Okay, so that's just a reminder of what we are discussing. I want to remind you of the relevant length scales that we, even though that they're very small length scales, hydrogen bonding interactions are extremely delicate in terms of two things: the underlying electronic properties, as well as the quantum properties of the nuclei. So, you know, typical OH bond, 1 angstrom. I say this for the diploma students. You know, now you've had an exercise in the molecular dynamics to write a code to compute this G of R, so the radial distribution function of the OH. And so if you've done it already, you've already seen what that G of R gives you. The water is a tetrahedral geometry, so it's not linear, which gives it a dipole. That typical angle is about 108, 109 degrees. And when two dipoles or water molecules orient relative to each other, there are two coordinates that, so if you were, you know, if you were thinking about how can I come up with a simple model that would allow me to capture the main interactions or the main degrees of freedom along which the interaction changes a lot. The typical ones are the distance between the two oxygen atoms and the orientation. Okay, so the distance and the orientation are the two main parameters that people use to parameterize interaction potentials for atomistic models of water. And so at some point in your life, you will likely have to maybe not run a simulation of water, but you may have to interface with different water models. And these are some of the parameters that are tuned to reproduce either electronic structure properties or experimental quantities. Okay. Finally, the third reminder, we discussed this right at the beginning in the first class. All these pictures that you see in chemistry and in biology of hydrogen bonds, or where protons are of course static, and even at 0 Kelvin, 0-point energy fluctuations of the proton are significant. So they are on the order of 0.3 of an angstrom. Okay. Now, just to give you a feeling of what 0.3 of an angstrom, it may seem like a small number, but it's actually a very big number in terms of how it can change electronic properties. And so just to give you a sense of that, so don't worry about this. This is an electronic structure study where what they do is they try to disentangle the total interaction energy between two water molecules, two particles in general, into the electrostatic energy, the exchange energy, so Pauli's repulsion, induced polarization, dispersion, van der Waals forces, and finally they include some higher order Hartree-Fock corrections to this interaction energy. And it's sort of hard to see in these tables here, so I show you a plot. They take this dimer, okay, so this is the object that they're looking at. They're taking this dimer and they're varying the distance between the proton and the oxygen, okay? at a fixed orientation. And using this energy decomposition approach, so you can, in electronic structure theory, you can use methods that allow you to decompose the total interaction into the various contributions. What you see here is that this is the percentage contribution of the electrostatic energy and the induction energy. So this is the polarization. So these are the two attractive parts of the binding energy between two waters. And you notice that as you squeeze in shorter, as you make the hydrogen bond distance closer, meaning when you move to the left, the electrostatic energy goes down by a significant fraction and the induction energy goes up. So polarization increases significantly. So, and the other thing you should take away from this is that, yes, 70% of the contribution of the interaction energy is electrostatics, but there's a significant fraction of it that is induced by electronic polarization, okay, which is typically something that's missing from most classical based force field approaches to modeling biological systems. Now, I also put the thermal de Broglie wavelength here on the right of the proton, 0.3 of an angstrom. So the picture that you should have in your mind is the following, right? So I have this dimer. In the classical world, these protons are, let me go maybe here. These protons are in one position, right? But when you account for quantum fluctuations, this proton, of course, is more spread out. It's more delocalized. So there's an uncertainty in where you can find its position. And if you go back now and you look at the underlying electronic contributions to the energy, you see 0.3 of an angstrom is a sizable fraction on this scale. And so the take-home message here is that quantum fluctuations of your proton along a hydrogen bond will have a significant impact on the underlying electronic contributions to the interaction energies, okay? This is something that is still essentially really uncharted area, because there's two worlds here in physics. You have the people who are doing a lot of electronic structure stuff. Then there are the people who are more in the quantum realm of things, and the two communities are still not interacting. Let me put it this way: there's a very small community of people who are actually worrying and thinking about these issues within the context of biological systems. Okay, so that's, even though most of our discussions are about assuming classical electrostatics, there are regimes where it works better and it's fine, but there are certainly regimes where it doesn't. And especially when you start to build very short range interactions, which happens in biological systems, these things actually matter. Okay. So finally, this is a final reminder of something that we alluded to, and I think we discussed as well, and it's related to the point of electronic polarization. The dipole moment of a single water is 1.8 dBi. And when you put that water in the condensed phase or in ice, the dipole moment enhances by a factor of about 2, roughly, well, less than 2. But the dipole moment increases quite substantially. And this is because of the electric fields from the medium polarize the the water and therefore enhance the dipole moment. And so most classical potentials that some of you might encounter for water artificially include this polarization by enhancing the partial charges of the atom. So it's most models out there do not account for this this polarization explicitly. Okay? In contrast to when you do electronic structure type calculations. Okay? And so probably in the next class, we'll actually go through more carefully on the different types of approaches to molecular dynamics and water models, covering ab initio and as well as classical approaches. Okay, so good. So now let's. So
Sorry, Professor.
Yes, please. Oh, go ahead.
In the previous slide, what is that unit, ESU?
It is. Let's see. Good question. ESU. I think it's basically debye. So debye is a what? Is length times electronic charge. So that's down here. I don't remember at the top of my head. I'll have to tell you later what it is. Okay, but it's one debye is 10 to the minus 18 ESU times 10. So it's probably some standard unit that, yeah, I don't remember at the top of my head.
Okay.
Okay. Okay. So, okay. So now we've reviewed basically some concepts about hydrogen bonding interactions and the importance of electronic and quantum properties. So now let's now look at something more basic, which is the phase diagram of water. So water, as you all know very well, has a very rich phase diagram across the temperature range of between 0 to 100 degrees. It can exist in 3 phases: solid, liquid, and vapor. There are regions that are, of course, in the phase diagram that are more relevant to biology. Now, okay, here's a question. So what are this? When we look at the phase diagram, there are several things that we like to pay attention to. And in the context of water, there's the boiling line, so the boiling curve, so coexistence between liquid vapor. There is the freezing curve, so coexistence between ice and liquid water, and then there's the triple point where the 3 phases coexist. Okay, so what's peculiar about the phase diagram of water compared to other liquids, other materials? Wait, I want to ask Herv. Are you there, Herv?
So it's called Hervi.
Hervi, sorry. But I guess he understood. Okay, let's try someone else. Let's see. Olaya. Olaya, are you there?
Yes, I can hear you,
Yeah.
sir.
Okay,
Please,
so
can you repeat the question?
okay, the question is, when you look at the phase diagram of water, does something about it make you wonder about what's particular about it? Is this what you'd expect for all materials? How the phase diagram looks? So let's say I gave you another liquid like ammonia or methanol. How do you think the phase diagram would look? What would be different?
I would express the critical point to be different because they are made of different components, and then some other factors, they won't be the same.
Okay, well, sure. The temperature and pressures at which different where the critical point might be will of course be different. Yes, that's for sure. But is there something else that you can recall? The hint is related to the phases. So, and in particular, the solid liquid phase. All right, let's try. Julia.
Yes. Can you hear me?
Yeah, I can hear you. Go ahead.
Yeah. I can say that if it is related with the phase, here I can see that the liquid phase occurs at higher temperature than the solid phase. I'm not sure.
Okay. Okay. So,
Sorry,
sure.
sir.
Yeah.
Me, what I see, Petulia, is in fact a question.
Yes. Okay. Very good.
Okay, because when I look at, I wanted to ask you why is this freezing curve has a negative gradient?
Very good. Very good. Okay. So you answered the question. Why does the freezing curve have a negative slope? Okay, very good. So Paul, you answered the question. So what's peculiar about the phase diagram of water? Well, the fact that the freezing curve has a negative slope. dp dt is negative. Okay, we're going to explain why shortly, but if you take most other materials, as Paul just correctly pointed out, it's this object here. This is negative, but in most other materials, dp dt is positive. Okay? And this is one of the, sort of give you the physical answer now, but this is of course related to why ice floats on water. Okay, so now, can anyone remember? Okay, well, let me go back to you, Paul, since you pointed this out. Do you have an inkling on what's the explanation? Where does it come from? How would you explain it?
Yeah. I don't know, but I don't think, is it related to the anomalous behavior of water at low temperatures?
Not so much. I mean, it is related to the one anomaly, which is that ice floats on water. Okay, but so it comes from thermodynamics. And okay, so let me remind you. So you all remember the Gibbs-Duhem equation. Okay, the Gibbs-Duhem equation is an equation that you all learned in thermodynamics that relates changes in the chemical potential of a substance, of a material, of two things in equilibrium to other thermodynamic variables or derivatives of those thermodynamic variables. And it's basically this first equation here. Okay, so that's the Gibbs-Duhem equation. You can make these all molar entropies, molar volumes. So that's the S hat. And if I have two phases in equilibrium, then the chemical potential must be the same. So now let's look at derivatives or a small change in the chemical potential of phase A and a small change in chemical potential of phase B. And we know that the partial mu A must equal the partial mu B. And what this essentially then leads to is that you can relate the derivative of the pressure with respect to temperature to a derivative of the entropy with respect to volume. Okay? And so this is known as the Clapeyron equation. And so forget about this last thing. This is not so important for this discussion, but the main story of understanding this is this first part here, which is that slope, this guy here, the sign of the slope is related to a ratio of the change in the entropy over the change in the volume between the two phases. Okay, and so we know that the change in the entropy to go from solid to liquid, there's an increase in the entropy. So that's a positive value. In order to get a negative derivative, a negative slope, the change in the volume must be negative. And so, and because the change in the volume is negative, what this means is when ice melts, it contracts. And this is why ice floats on water. But this is this slope here being negative is what makes it in the pressure temperature phase diagram of water is what makes water anomalous. This is all from the language of thermodynamics. Okay, and but this of course tells you nothing about what are the microscopic molecular hydrogen bonding fluctuations and interactions that are associated with these anomalies. Okay, but this is something that makes water very unique, and so there's been a lot of work in, especially in the statistical physics community, in trying to understand how to relate these changes in entropy and changes in volume to microscopics. Okay, so how do people understand these changes in thermodynamic quantities to microscopic molecular scale fluctuations? Okay. Now the standard, sort of the holy grail of understanding microscopic fluctuations and in understanding the theory of liquids is something known as the radial distribution function. Okay, so I'm sure all of you now have already seen this. So I have a liquid that's held together by many different types of interactions, and what one wants to do is ask, what is the probability of finding two particles in the liquid at a particular distance? And this is a very, very important quantity, and you'll see shortly why. And it's very important because it is a quantity that allows you to, from the microscopics, to go back to quantities like the pressure and the entropy and the volume. Okay, so you can relate properties in the pair correlation function in the G of R to some of these microscopic thermodynamic quantities. So there's been, especially in the statistical physics community, there's been a lot of effort in trying to understand liquids first in terms of these pair correlations. Okay, so what is formally the radial distribution function? Well, essentially, it's very simple. You have n particles, so small n, the capital N is the total number of particles in the system. Small n is the number of particles you want to look at for the n particle density. And the G of R, the n body G of R, okay, radial distribution function, is a joint probability distribution of the n particles divided, normalized by this object here at the bottom. And what this object here at the bottom is, it's a product of the single particle densities. And so if you have n particles and you separate them up, to infinite distance, then the probability distributions become independent. And so the joint probability is just a product of the individual particle densities. And so the G of R is the pair correlation function is a two-body density. But in general, what one can get from either Monte Carlo or molecular dynamics simulations are the n particle densities. They're horribly difficult to converge and to extract, but in principle this is possible. But so the G of R is the two particle density, and it depends on simply the distance between the particles. And so it's just a probability distribution, and when the particles are far enough from each other, they're normalized in an appropriate way, so that the G of R goes to 1. Okay, so that's basically it. And okay, so how does a G of R typically look like? So you've seen this in Leonard-Jones liquid. You've seen this in water. And if you look at the G of R in a liquid, it will have these types of structuring. Okay, so and these layers essentially correspond to are attributed to different shells of particles as a function of distance from your center. They're often called the first hydration shell, the second hydration shell, and oscillations in the G of R imply correlations. Okay, so when I move far enough away, this will be flat, so correlations will disappear. As I come closer, the particles feel each other. Okay, and when they feel each other, this leads to some structuring in the correlation function. Okay, so now let's do a simple. So let's actually what causes the structuring? What causes the correlations in? What's the physical origin of the correlations in the G of R? And so one way to try to understand this, and this is what people who've studied theory of liquids have done, is to compare two systems. So let's compare the G of R that you get from a Leonard-Jones liquid. So Leonard-Jones is, well, you know what Leonard-Jones is. It has a repulsive R to the 12 and an attractive R to the 6. So imagine that you were able to do Monte Carlo or molecular dynamics with Leonard-Jones, okay? And then you compute the G of R, the two-body G of R, and then you do the same thing. You repeat the exercise, but now you do it for hard spheres. So hard spheres is has a potential where below some distance it is repulsive. Okay, so at R less than or equal to some sigma, some excluded volume, excluded distance, there's a steep, right? So it's a vertically upright potential, it goes to infinity, and then above that distance it's flat, so it's 0. Okay, so it has no attractions. Hard spheres has no attractive interactions. Hard spheres just has a repulsive wall, essentially, a reflective repulsive wall at some sigma. Okay, so now the question is, how do you think the pair correlation function will look like for the two systems? Do you expect them to be the same? So let's see, who can I ask now? Romina.
So I would think, since the Leonard-Jones has an attractive term at a certain distance,
yeah,
the probability at that distance should be higher than in the hard sphere case.
Okay, so
to find other particles in that distance.
Okay, so now let me, in this picture that we had, let's go back. So here, so let's say this is Leonard-Jones liquid.
Okay.
How would you change this for hard spheres?
Okay, this is R over sigma, so it's just this is some kind of standardized R.
Exactly. Roughly, yeah.
Roughly.
Yeah.
Okay, so this really high probability peak, no, this really high G of R peak here in the front, that shouldn't be there, I guess.
Okay, so what good. And what, so after this, what do you, so let's say that sigma is 1.
I don't even know if the fluctuations would be there, and if it's only a hard wall, maybe it would just.
Wait, okay, hold on. So let me just walk. Okay, so on the one side, you think that these oscillations might not be there.
Yeah, but I really can't explain it mathematically. I'm not good enough with functions.
No, it's okay.
Yeah.
It's good. I'm less interested in the functions and more. What's your intuition on?
So it should also be 0 in the very small r over sigma, because there is a hard wall, so there can't be anything.
Exactly. Perfect.
And either it rises then and asymptotically, probably it rises then and asymptotically goes towards some value.
So you're okay. So let me just interpret what. So 0, then steep rise, and then you expect something flat, maybe.
Yes.
Okay.
So either that, or I don't know if the probability would also be smaller close to the hard wall because they repel each other. But yeah, something.
Yeah,
like that.
I see. Okay, so that's okay. That's partly correct. Partly correct. So the intuition. So definitely, because it's a hard wall that goes to infinite potential, there is 0 probability of finding it less than or equal to sigma. So it will be a step function here. Okay, now the curious thing is, so actually my intuition would also say, if I have a hard sphere, there are no attractions.
Hello?
Yeah?
Can I ask a question before?
Is it related to what I'm saying or something else?
I think it's still on the graph, so I don't know.
Okay, so let me just finish what I'm saying, then you can ask. So so my intuition would tell me that if I have a hard sphere without any attractions.
Sorry.
Yes.
Yeah, before I go on, but when I look at the next slide, you said the 0v is after a certain, for r or greater than some sigma.
That's correct.
So the 0 is, I think, should be after 1, not here before.
No. Okay, so Palush, that's just so yeah. Don't take this plot literally. It's so we could make this sigma. It doesn't matter. We could make a sigma at less than 2, less than 3, less than 1, less than 0.5. Doesn't matter.
Okay.
Okay. So let me just finish, and then I open for questions. So my intuition would tell me that if I have no attractions, then these correlations would possibly just go away, because my intuition would say, oh well, it's attractions that in this, the -1 via the 6, for example, that would induce structuring in the liquid. Okay, so Valerius, go ahead.
Yes. So I don't understand what do you mean by hydration shell, and also perhaps I don't know, when you say the attraction goes away, does it mean the correlation function for the hard sphere will be like a delta function? Because
okay, so let me clarify. I haven't. What I told you was my intuition, but my intuition is wrong. First of all, so I haven't told you what happens in the hard sphere. So you have to just wait a bit for that. So let me answer first your question on the hydration shell. let's see. Let me try to, if I can. Okay, no, so I don't have a nice picture here to show you. Maybe I can use just this. Okay, so the hydration shell is the following. So basically, this R is looking in a radial coordinate, right? So I sit in a central particle, and I'm looking as a function of growing a sphere around me, the probability of finding another particle. And so the hydration shell essentially is a term that corresponds to if I look around me with a growing sphere, it will touch the first coordination shell or particles, and then as I grow the sphere bigger, it will touch the second coordinated particle, second shell coordination particles. So it just corresponds to the layers that form the coordination spheres around the particle. Okay, is that clear?
How do you form the correlation sphere?
So sorry, I can't hear you, Valerius.
So how do you form the correlation sphere exactly?
How do you form the correlation sphere? Okay. So, the answer to that is in what the G of R is. Okay, so the G of R is a two-body probability density of finding two particles at a particular distance. So you tag one particle and you ask, what is the probability of finding another particle at a particular distance? Okay, and then of course it's normalized in some fashion that I described earlier, but depending on the distance of your other particle, there will be structural correlations between the tagged particle and a particle that is close by, whereas something that's very far away will, of course, it should not be correlated to the central particle, right? So these measure structural correlations, and these structural correlations, what we're trying to ask now is, where do they come from? Does that answer your question or not really?
I still don't quite understand that well.
So okay, to explain what exactly don't you understand?
Maybe some of the terms. So
Okay.
I think I will just listen.
Okay. Maybe it will become clearer as we move along. Yes.
Yeah, I still don't get quite well here. If we are talking about the attraction bit of it, so why is it starting with 0 here?
No. Okay, Pelush, let's wait. Let's you're confusing interaction potential V versus when I use the V and I do thermal sampling and I generate configurations with a specific Boltzmann weight, those configurations can be used to construct a probability distribution. So this plot that I'm showing you here is not the Lennard-Jones potential. The Lennard-Jones potential is what goes into the potential from which you then generate configurations with a Boltzmann weight. Those configurations then are used to construct an n particle probability density, or in general, in this case, a two-body probability distribution. Do you see the difference?
Fairly somehow.
Okay. So well, have you done the exercise for the numerical 2 yet on the G of R?
I'm still doing it.
You're still doing, okay. Once you're done with that, this will make more sense. Okay?
Okay.
Okay, good.
Sorry, Professor.
Yes, go ahead, Maha.
Yeah, in relation with that, can you here explain the zero? I mean, in this case.
So, can you speak up, please?
Oh, sorry. Can you hear me?
Yeah, now I can.
Okay. So here I said, can you say something about the zero correlation? In this,
yeah. Okay. Very good. So, okay, let me do that. So, okay. So I have a liquid. Let's say argon, right? And the fact that there's zero correlation here means, or zero probability means, if I take two argon atoms and I try to bring them, squeeze them closer and closer and closer together, they're going to feel Pauli's repulsion. There's going to be an electron cloud overlap. And so they're going to be very steeply rising repulsive potentials. So what that means is that there's a very low probability of generating configurations that will explore those regions. And because there's a low probability of exploring those regions, those things go to zero in that region.
Okay, so, and it's not like when you increase the distance, the correlation function increase, because here we see that it goes to 3 and then to 1.
Go okay.
Yeah.
Yeah. So okay. So okay. So let's take two situations. So we understand now that there's basically low probability to go very close to each other. Okay. So now I start to move the particles away from each other, and eventually they're going to sit in the minimum, right, of the potential. And now as I begin to move them away from each other, okay, so let's not forget, so now these are they're thermally populated, so the thermal fluctuations, and at some distance in the nearest neighbor, for example, there's a high probability that these two particles are going to want to interact favorably with each other. Okay, probably close to the minimum. It doesn't have to be at the minimum, but probably close to the minimum of the potential energy surface. Then as I move further and further away, well, that probability is going to reduce because there's an excluded region of volume in the liquid. Then I will hit my second shell. In my second shell, there's going to be then some increase, an enhancement in the probability of finding a particle at that position. So now, one way that will help build your intuition on this understanding is to ask the following question. How would this change if you were in the solid phase? So this is a liquid that I'm showing you here. Now let's ask, if I ask the same question, how does it look like in a solid? In a solid, what you would see is you'd have, okay, that'd be again 0. Then you'd have a very, something like a delta function. So it'll be a very sharp peak. And then it would it remain non-zero here? No, it would go to, zero. Exactly. It would go to 0, and then there'd be a 0 region, and then there'd be another delta-like function. Okay, so now you see where it comes in the solid, right? Okay, so now ask yourself, if I take the solid and I begin to inject kinetic energy into it, and I heat it up, then the thing starts to jiggle and wiggle and get more disordered, and then all those regions that were completely 0 probability start to get thermally populated by some Boltzmann factor.
Yes.
Okay, is that? Okay, very good. Very good, very good. Okay. Now, let me just mention here in passing, some of you might already know this, but this G of R is directly related to a free energy. A free energy, or it's often referred to as the potential of mean force along the distance. And it's related to that by, the logarithm of the G of R times thermal energy gives you the free energy. And if you do that, you'll see it's just the inverse of this, right? So the maximum of this probability will become a minimum in the free energy. And that's where there's a high probability or particles like to spend a lot of their time in that free energy minimum. Okay, so that the two are related.
Sorry, Professor.
Yes, Pooja.
I have a question. This kind of excluding region that we are taking here, 0 to 1, yeah. Then this kind of excluding region occurs for every molecules, yeah. Or
Absolutely. So as long as we're not dealing with plasmas, yes. It's not the same for different molecules. So different atoms have different sigmas. So if you took argon versus xenon, their sigma is not the same.
yeah, but not the same. But there is at least some kind of excluding reason, yeah.
That yes, because all of these systems have Pauli's exclusion is in all the systems. Okay. So it must be there.
Yeah. Okay. Thank you.
Okay. Okay. More questions about this? Okay. Very good. So let's go back to hard spheres. So how would the G of R change for hard spheres? And what's interesting, and this is a bit of it might come as a surprise, is the following. So this is the thing that we were discussing with Romina. So in a hard sphere, if you computed the G of R, there would be basically a step function here, because there would be 0 probability of going below sigma. But then you get these oscillations. That's interesting. So and not intuitive at all. It's not something I would have expected. And of course, of course, the nature of the oscillations are different in a Lennard-Jones like liquid versus in hard spheres. But basically, what this is saying is that the short range oscillations in this GOVAR in a hard sphere fluid is not affected. Let's say the qualitative trends first in the oscillator are not affected by the attractive forces so much. It's more to do with geometry and packing. So basically, if you were to take, I don't know how many of you eat cereal or know of Cheerios. Cheerios is a type of cereal, right? It looks like benzene rings. If you were to compute it's like a hard sphere. If you were to measure the GOVAR of Cheerios, they would have also this short range. But this short range structure has little to do with attractive interactions and more to do with geometrical packing. Okay.
Yeah, I have a question.
Yeah, please.
I thought that in the hard sphere, the second peak also should be like sharper than the Lennard-Jones potential.
Not really. Well, yeah, sharp. Yeah. Yes, sure. It is. But wait, why do you think it's going to be sharper?
Because we don't have a wide range of interaction as before. So it should interact in a certain distance. So we hardly find a sphere.
Yes.
Within that region that there's no interaction, right? Like from
It's yes. Yeah, that's a good point. And I mean, actually, I never thought of that, but if you look at it carefully, it is true. This the hard sphere looks like it has a tighter potential than the higher curvature than the Lennard-Jones one, which is softer. So yes. Yes.
Okay, but actually I expect it like sharper more because so it does interact in the sigma distance of sigma. So
yeah, but so okay, that will affect that will depend a lot on temperature. It'll be affected a lot by temperature, and I think it'll depend on temperature, depend a lot on the phase, how the phase diagram of the hard sphere looks like, depending on the sigma one is chosen. And I forget now what temperature these things were done at for the left plot. So I agree with you that modulo same sigma, or let's say modulo using the same sigma and the same temperature, I don't expect it to be like sharp like this first peak, but yeah, possibly sharper. Yeah. But as you turn on temperature, it will start to smoothen out that second peak as well. So yeah. Okay. Okay, so this should surprise you. Well, like it surprised me, at least when I first saw this, which is that a hard sphere short range layering is very similar to not very similar, it has similar qualitative features to a Lennard-Jones liquid. And And so this is why in the statistical physics community, there's been a lot of interest and work in understanding hard spheres and the phase diagram of hard spheres, and trying to use that to learn about liquids. Okay, so okay, we'll stop here and we will continue next time. What I suggest this as a simple exercise for all of you, especially if you're not so familiar with these pair correlation functions, is try and construct a sketch of the pair correlation function for solid ice, liquid water, and water vapor. And I think the exercise will help you understand a bit better where the potential comes in, where the interaction potential comes in, and then where the thermal probability canonical weight of the configurations and how that generates then the pair correlation function looks like. Okay.
Sorry.
Yes.
Do you have a picture of the potential for the hemisphere there?
Do I have a picture? I want you to try and draw it.
Ah, okay.
Try. So with what I've given you here, you should be able to draw it yourself. But you don't need the, okay, okay, the potential should guide your discovery of this. Okay, but in any case, the answer is already here. But what I suggest is, for example, this is a liquid. Let's say it's the pair correlation of water. Do the same thing for ice, and do the same thing for the gas phase, for vapor phase. And well, you will see obviously that this is let's say the simplest, most trivial order parameter that one can use to identify phases, right? Okay, because that's how do you identify phases in different materials.
Excuse me, can I ask you a very quick question?
Sure, go ahead, Jonah.
Yeah, maybe these are very stupid questions, but just to be sure,
No.
I could actually research it myself. But
no, please.
Yeah. Okay. So, what is exactly the difference between radial distribution function and pair correlation function? I see this.
It's the same. It's the same.
Yeah, the same, right? Okay.
Yeah, it's the same. It's the same. It's the same. Yeah.
Okay.
Yeah.
The other thing is that I see that most times people try to do a Fourier transform of these things.
Yes.
Particularly discussing structure factors.
Exactly. Okay. Perfect. Yeah. Yes. So basically, the structure factor is the equivalent in case space of the GeoVar, where you take the Fourier transform of the GeoVar. And why this is useful and done is because when one does X-ray and neutron scattering, what you extract from those experiments are structure factors.
Oh, I see.
So you measure things in Fourier space, and then if you want to, get back into real space, the object is the GeoVar.
Oh, okay.
Okay.
Yeah.
Okay.
Thank you.
Thanks, Jonah. Okay, that's it for today. See you on Thursday, and I'll try to have your quizzes graded by then. All right. Thanks, guys.
Bye.
Ciao, ciao.
Thanks. Bye-bye.
Thank you. Bye-bye.